Hello, I'm Lulu Miller. If you joined us last week, you met the hidden body part stowing away inside your body. And today we have another hidden story about life and non-life and how the line in between them is way blurrier than we might think. We are talking about viruses today. This episode is a rewind, but it's a lovely one. It's called Shrink. And what I love about it is not just that it busts a binary between life and non-life that I always thought was hard and fast, but also that as you listen, it really feels, at least to me, like Robert Krulwich and Jad Abumrad, OG hosts, that they kind of shrink down into these little boys who are so giddy with questions for Carl Zimmer. It's like I picture them like two little boys at Santa's knee, just taking in the knowledge. And it's a really raw, lovely glimpse, I think, at what this show does best when it does its best, which is to make space for questions and for real listening. So I hope you enjoy this kind of giddy romp through the evolution of life and non-life and all the places where that line blurs out a bit. Here we go.
Wait, you're listening? Okay. All right.
Okay.
All right.
You're listening
to Radiolab.
Radiolab.
From
WNYC.
See?
Yeah.
Rewind. Come on.
He's totally
you guys
like
came saying we want to talk to you about three
radio
things.
jock.
Okay. Let's do that. Let's do that
Okay,
then.
you have to keep
But
up
we
with
can't
this.
do-
Hey, this is Radiolab. I'm Jad Abumrad. We're going to do something that's a little bit unorthodox today, at least for us. If you've listened to the show in the last 10 years or so, however long we've been doing this, you understand that we like to edit, right? We like a good edit, or 70. But today I want to play you something that has almost no edits at all. It's just a conversation, which is, of course, the foundation of what we do. These long, rambling, occasionally profane, error-strewn conversations that we then edit into something coherent. But today, I want to show you the messiness. No edits! This is a chunk of a conversation with science writer Carl Zimmer. He came and sat down with us a while back, and we talked for 4 hours. 2 of those hours became the basis for the CRISPR podcast that was a few podcasts ago. This was about gene editing. But then we kept on going for another 2 hours, and he told us this story, actually 2 stories, but we're only going to play one, that I thought was really cool. And it's about this new way of looking at life. Is this a long story, a medium story, or a short story?
It's not a. We can get through this a lot faster than CRISPR.
Okay.
Okay.
I really like CRISPR, by the way.
So do I.
I'm into
CRISPR
it.
is, it's the bomb.
Yeah, that's a perfect way to describe it.
Biological bomb.
Okay, so chapter 2.
Okay, maybe you could start the story. Once upon a time.
Sure. So, once upon a time being, I'd say once upon a time being before 2003.
Okay.
We basically had 2 kinds of living things on Earth. We had cellular life and we had viruses, and it was nice and distinct and clear cut. And so cells included us, because our bodies are made of cells, and bacteria, which are single-celled, and all the other things that can grow and let their cells divide. They have DNA, they have proteins in them, they have all that stuff. And then over here, you had viruses. And viruses were just little packages of genetic material that would go from cell to cell and use the cell to make new viruses. And so inside of them, all they had were genes and a couple proteins that would then just sort of hijack their host.
I mean, they seem like so preliminary that they don't maybe not even qualify as life.
Right. They can't grow on their own. They can't generate their own energy. So, us and all other cellular life, we make a kind of a fuel called ATP. And we need that to do every little thing in our body. And viruses don't make ATP. So, they're...
So couldn't we say that life is us, cells, and multicellular beings, and then there's sort of pseudo-life, which is these little things that live off of us?
Yeah. A lot of scientists don't really think viruses are truly alive. They just sort of take advantage of life to make more copies of themselves.
Okay.
Can I ask a dumb question? So viruses, they don't have a wall around them in the way that cells are walls, essentially, are walled off areas?
They might have a protein shell.
Uh-huh.
And so, when the flu virus goes into a cell, that protein shell kind of breaks open and the genes and proteins inside come out.
They do have containers that contain them for a while. I see.
Mm-hmm.
Well, isn't that one of somebody who had a list of rules that make you alive, and wasn't a container was one of those rules?
Yeah.
But
Yeah,
I mean, they don't do the
that's-
energy, but they have the container at least.
Right. So the problem with viruses is that they have some of the things that we think are essential for life, but not quite all of them. So it's been convenient just to say viruses are not alive.
Mm-hmm.
Just put them over there because they don't have everything that cellular life has. So we'll just say they're not alive.
Okay.
They're just viruses.
Gotcha.
And then?
So then what happened is that there was a scientist named Timothy Robotham in England who was investigating a outbreak.
Timothy Robotham.
Timothy Robotham.
That's
yes.
a good English name.
Robotham with a f.
Timothy Robotham was working in Bradford, city in England, and he was looking at the kinds of bacteria that might be growing in a hospital. Like they were having some problems with pneumonia outbreaks and so on, and he was like, okay, well, what's growing around here? And so he went to a sort of a cooling tower for water on top of the hospital, and he took a sample and he went and put it under his microscope, and he's like, some interesting bacteria here. Oh, here's a very interesting bacteria that doesn't really look like anything I've seen before.
Wait a second, this guy would just kind of crawl around to weird places and just snatch little snippets of scum, or what would he?
Yeah.
What was he? What was his job?
He's a microbiologist.
Oh, of course.
So, it would be good to know. Like, I mean...
Is that what microbiologists do? They just go scrape little bits of rock or water tower
They search the
scum?
world. Yeah. I mean, microbes are everywhere. So microbiologists go everywhere to find microbes. So they're even, in a water tower on a hospital.
Was he in a kind of an investigatory role? He was trying to help them figure out which bacteria are making people sick?
That was one of the hopes. But, he was thinking of doing a survey because, there are diseases like Legionnaire's disease, which can, grow in these sort of containers of water. There's some concern about that. So, better to get to know what's growing. So he's particularly taken by one thing that he assumes is bacteria, and it's got a kind of interesting kind of roundish shape. And when bacteria are round, you can call them cocci or coccus. So he names this Bradford coccus, gives it a name.
That's why the coccus name comes from? It's referring to the shape? Mm-hmm. Like streptococcus? Mm-hmm. Is it because it's round?
Mm-hmm.
Well, I did not know that. The things you learn when you talk to Carl Zimmer.
Learn.
My God. Okay.
So he's trying to study this thing, and he's trying to. So when you're a microbiologist, the way you study bacteria, you get them to grow, and he can't get this to grow. He's feeding it things, and it's like it's not growing. Why is it not growing? I can't figure it out. And eventually, he just hits a wall, and unfortunately, his lab got shut down, and so he basically said, "Okay, I don't want to." Throw this stuff out. So I'm gonna give it to some of my colleagues in France.
It wasn't dying, it wasn't growing?
Yeah, so he gave it to a scientist named Bernard Lascola and his colleagues. And they kind of put it
Bernard Lascola.
Oui, and he just says he just sets it aside for a while and doesn't, it's just more bacteria, and it's for some reason he decided to take a look at this Bradford coccus. Like what was this thing that Robotham was talking about? So he looks at it and he says, "Okay, this is the size of bacteria, but it looks like a gigantic virus." What
is a gigantic? A virus is usually very small.
Exactly.
So a bacteria to a virus is like
like hundreds of times bigger.
Hundreds of times. Okay.
So it's the Queen Mary to a small dinghy.
So he looked up close and he was like, what is this thing? This doesn't look right. This. If I didn't know better, I'd say this was a virus.
He's saying this based on its internal orientation?
Its appearance.
It's because it had the protein thingy, it had the stuff.
So a lot of viruses, they have a shell made of protein, and the shell is kind of composed of plates. So it kind of looks like a soccer ball.
Ah.
So it's a very distinctive look.
Okay. And it looked like that?
It looked like that. Didn't look like bacteria.
Oh, interesting.
It's like, wait a minute. Could this be a virus?
So this would be like maybe like finding an enormous soccer ball in the woods.
Yes.
So he'd found the Leviathan equivalent of a virus.
Right. It didn't make sense. It was kind of crazy in that microscopic realm to say maybe this is a virus.
Wait, so Brad Mumford, what's his name again?
Timothy Robotham.
Robotham didn't have this realization?
Nope.
He hadn't looked at it closely enough.
He looked at it.
But he just didn't somehow put that this is a virus.
It didn't click for him.
It was a
assumed it was a
Tuesday,
bacteria.
you know? Wednesdays
Other-
that's a virus day, and this was Tuesday.
And it's likely that other people were looking at these same things in years before.
I'm thinking they were bacteria, not realizing. Interesting.
Here's something the size of bacteria.
Well, in fairness, because viruses are always small, then you wouldn't think a big thing would be a virus. So.
Well, viruses are always small in the sense that they were discovered because they were small. So basically, what scientists did was they discovered viruses by filtering fluid from a sick plant or a sick animal through a filter, porcelain actually, and it was so small that anything the size of bacteria got trapped in the porcelain and anything smaller came out.
Oh.
And lo and behold, they could find things that could cause sickness in that fluid that passed through the filter.
Oh, so the discovery of viruses meant it was innately small because that's how you filtered for them.
That's what they were looking for.
That's interesting.
So there were probably generations of scientists who were looking at it through microscopes, saw some interesting round thing and assumed it was bacteria, and it was probably a virus.
What the fuck is this giant Leviathan virus? I assume that was his question.
Well, I mean, he had to really establish that it was. And so what happened was that he looked very closely at it and kind of worked out its chemistry. And the more he looked at it, the more it looked like a virus. They started actually looking at its DNA, which hadn't been possible before. Turned out that its DNA resembled the DNA of viruses and not of any known bacteria. It didn't have the equipment for making fuel inside of it. And then the real kicker was that he found out how to grow it. What he had to do was he had to stick this thing inside of amoeba. And then out of the amoeba would come more Bradford coccus.
Just like a virus.
Exactly like a virus.
So you need to change the name from Bradford coccus to something else.
Right. So they named it Mimivirus.
Mimivirus.
Mimivirus? Mm-hmm. Because they were in France, and Mimi is in a French opera.
Because it was a mimic. It was mimicking.
It was a mimic.
Yeah.
Oh, interesting. Mimi. Is
like
that French for
like a
mimic?
mini me.
Mimi? Is that like a French word for mimic?
I think they just took the beginning of mimic and added it to virus.
Huh. Mimivirus. Very nice.
I guess it's the same thing twice. Mimi. It's like mimic. Yeah, okay. I get it.
So,
interesting.
Yeah.
Wow.
So this was really bizarre when they published the report on this in 2003, and people really scratched their head because remember, ordinary viruses have maybe 10 genes. This one had 1,018 genes in it.
Wow.
When you have 10 genes, those are the genes that so you have a protein capsule, and so you can swim through the thing. So when you land on a cell, you can burrow in and then explode and then make babies. So there's not much to being a virus, and you just need a few genes for that. Why would you need 1,000? What did you say?
Does this thing have particular talents that the other viruses didn't have?
Yes, maybe it was like
it does.
It does.
Oh, it does.
What
okay.
Is, okay.
Well, so one thing that's really interesting is what happens when it goes inside its host, an amoeba. It goes in, but instead of kind of shedding off that protein coat and just spilling out its contents, it actually goes in and stays as it was.
You mean it stays
and-
in a container and everything? Just sort of.
Yeah.
Oh.
It's called the virus factory. Once it's inside there, it's this thing they call the virus factory. And it basically is able to things, components come into it, and then it sort of it has enzymes that can refashion them, and then out come the components for new giant viruses.
So it doesn't have to go into the nucleus of the already existent cell?
No, it just floats in there.
Oh, interesting. So it what does it do? Like,
like builds
open
a little
open a portal and it sucks up some stuff. And
Yeah, it has this beautiful sort of they call it a stargate because it's shaped like it's a doorway shaped like a star, and things come in, and then out another stargate. These sort of manufactured things come out, and then in the cell they assemble into new giant viruses.
Oh, so it spits out the raw materials and then self-assemble into a giant leviathan?
Mm-hmm.
No, baby giant viruses, which then, how do they get out of the, do they explode through the surface of the cell?
They just blow out. Yeah.
That's like a totally different thing
Never
than
heard
a virus.
of that. Yeah, I thought normally viruses just go into the machine that's already there because they're parasites. They just use the living thing.
Yeah.
This thing is, I have a weird kind of respect for this thing.
Oh yeah, it's amazing. And one of the amazing things about it is that it can get its own viruses.
Really?
Yes. So there are viruses of viruses. These things are
Wow.
called virophages, and they actually go into the virus factory and hijack it.
Oh,
and instead
interesting.
out come virophages.
Oh, wow.
Oh, yeah. As soon as you have a virus factory, that's what a virus wants.
Mm-hmm.
So now that the virus has its own virus factory, well, it's going to get
Viralized.
viralized by the other viruses.
Right.
Weird.
Very
Yeah, weird is the right word, I think.
Right. Now, so in 2003, you could say, well, this is one weird virus. But these scientists said, well, I wonder what else there is. Like,
Well, did that sort of, wait a second. So they said, okay, it's got all this extra genetic power, but it's doing this sort of special circus act here. It's building its own factory, and it's just behaving differently from it. So maybe it just needs all those genes to do this special thing it's doing?
the problem was that when they looked at these, 1,018 genes, most of them didn't match anything anyone had found before.
These are new genes.
Genes, that you couldn't even guess at what they were at.
This has got to be from this is like an alien. This is from Saturn, this thing. Is that where you're driving with the story?
Not quite, but kind of. I mean,
So wait a second. So they look at all the gene. They look at the chemistry of life as it's known,
Yeah.
and they don't find any matches for this little thing, this big thing, rather.
for most of the genes, they couldn't find a match. You can look at,
Wow, that's a double mystery. Like, what is it? What is this, and where does it come from? Because it doesn't seem to have the smell of Earth life.
Yeah, except that it uses DNA. I mean, it
Okay.
uses protein. It uses our chemistry, but it's doing something weird. And so these scientists said, well, okay, they looked in an English hospital, water cooling tower. Let's go look at one here in France. And so they looked, and they found another giant virus, which was even bigger than the one that they had already found.
Where
the
was it in the
Mimivirus.
hospital in France? In the air
In the
conditioning
cooling
unit?
tower?
It was in
Again?
another cooling tower.
Jeez, so this is a cooling tower phenomenon so
Yeah,
far.
Rooftop biology.
Well,
Excitement galore.
it's more like the drunk looking for the keys under the lamppost. It's like that.
Oh, because it's wherever you look, there
It's
it
like
is?
we know there was giant viruses found in one water tower, so let's go look in another water tower. Like that's our safest bet. And hey, look, we found an even bigger one. Which had
An even bigger one.
It was even bigger, yeah. So instead of 1,018 genes, it had 1,059 genes. So they named this one Mamavirus.
Mimi's first cousin, Mama.
Right.
Did
right.
Mama do things in the cells that Mimi didn't do, or was the same, did it also build a
It was,
factory?
yeah, it was making a virus factory. So it's there's a common theme here with these two. Now you have two giant viruses doing the same thing.
Isn't this the whole Stargate and everything?
Yeah. What's weird is that the Mamavirus has a bunch of genes that Mimivirus doesn't have. So it's like, and again, don't match anything that.
So they don't
people
know
can
what these
figure out.
extra ones do.
Some of them look like they're involved in building proteins, which doesn't make any sense because viruses are not supposed to do that. So this is all completely confusing. But then they say, like, okay, maybe we need to kind of get away from the whole water tower thing and, widen our little...
Where would you go? Like, so the opposite of a water tower would be like the bottom of a well, or do you go to a library and look in the interior of old parchment books?
No, you start looking at places like you look in the ocean, or you look in sediment, or you look inside animals, or you look in the soil, and they start finding giant viruses over and over and over again.
Really?
Yeah.
In all those places?
In many
soil inside of animals, like in animals' tummies or something?
Yeah. So they went to these researchers went to Brazil and said, let's go look at animals and see if we can find giant viruses. And they found a new species in cows, and they found a new species living inside of a monkey.
Oh. And these were they finding giant viruses?
Yeah.
I mean, the numbers of genes were going up and up and
Yeah,
up.
they would keep finding new record breakers. So the biggest one right now is called Megavirus.
That's the summer movie.
Yeah,
Megavirus.
I mean, there's
Bigger than Mimi and bigger than Mama. Mega.
In a world.
In a world.
You got it. That's right. It's like the Truckosaurus. Like this is like I'm wondering what they're going to do as they keep finding bigger ones, because you keep having to find superlatives for these things.
Well, where was Mega found? And what was
Mega, I believe, was found in the ocean.
And how many genes does Mega have?
Mega has 1,120 genes.
Whoa, okay, so
But it's not actually so it has the most genes, but it's not actually physically the biggest giant virus.
Which one is?
So this one is called a Pandora virus.
It was found in a box. Let me guess. In a sealed box, and then they opened it, and oh my God!
Well, it has this bizarre shape like an urn,
Oh,
which is completely nuts. There's no urn-shaped viruses. This is crazy.
And the urn, did that remind somebody of the myth of what?
So Pandora's
Pandora.
box was actually an urn.
Oh, it was. Okay.
it
Yeah.
was.
Oh, I see.
Oh,
Yes.
why did we call it Pandora's box then?
God, that's a very learned.
Just to make you happy.
very
Because
learned
you'll
naming.
love where they found it.
Where did they find it?
So what they did was these Russian scientists they were collaborating with dug up frozen tundra that had been frozen for 30,000 years. And they said, let's thaw this out and see what's in there. What kind of things have been asleep for 30,000 years?
It sounds like the beginning of a sci-fi movie right there.
Yeah.
Among other things, they found
frozen land.
They found Pandora virus. And they not only did they find it, but when they let it warm up a bit, and then they gave it some amoeba to check out,
It did its thing?
It did its thing.
Wow. And how much bigger if the first giant virus you introduced us to was like an elephant-sized mouse? Compared to that elephant-sized mouse, how much bigger is this one? Maybe it's more specific than you want to be.
I need to look at the numbers,
Uh-huh.
but you're kind of going from elephants to dinosaurs. You're getting bigger and bigger and bigger. We're now talking about Pandora virus is bigger than a lot of bacteria.
Wow.
So wait a second. So these things are now being found everywhere you look? I mean,
They are incredibly common. They've even been able to get giant viruses out of people.
really?
Yeah.
We did what's
Where do you find them in a person?
in our intestines or something?
I believe they found one sample in somebody's lungs, and another sample was found in someone's blood. But it's really hard to tell whether they're actually actively invading us and making us sick. Maybe instead of invading amoebas, they can invade human cells. Because amoeba and human cells are surprisingly similar. Or is it just kind of along for the ride with some amoeba that infect us? Or does it kind of drift in, and when people are sick, their defenses are down? So we don't know if giant viruses have anything to do with human disease, but
It
Well,
strikes
what
me,
about-
though,
what-
you have a category problem here, though.
Yes.
If you've got a giant virus that's virus-like in its general shell, but it's making proteins, it's got a bunch of genes that viruses don't have. You're already bigger than some bacteria. Shouldn't we call it as its own separate thing at this point?
That's what people are arguing about right now. I mean, do we keep that line between viruses and cellular life and just put the giant viruses with the viruses? Or do we kind of blur the line a bit?
This feels like it's on its way from one category to the other.
So that's one of the big questions is like, what way did this thing go in evolution?
What does that mean?
Well, how do you get a giant virus? Like,
How do you?
how do you? Well, so
We'll get to the potential answer to that question, which I think is totally fascinating, after the break. Hey, Jad here, Radiolab. So we're going to return to our conversation with science writer Carl Zimmer. It's an unedited conversation. And we were talking about giant viruses and what they can teach us about life, which really starts with a simpler question of, like, where the hell did they come from?
how do you get a giant virus? Like,
How do you?
how do you? Well, so one clue comes from those genes. So now that they're finding more and more of these giant viruses, they're finding enough variety of them. They can look for sort of some common genes that they share, some common mutations in genes, and they're finding actually that it looks like giant viruses might actually belong to one lineage.
Oh, interesting.
Oh, so they're cousins. They have a common ancestor?
Yeah,
So it's a tribe of a sort.
right, and if that's true, it could be an incredibly old tribe. These giant viruses could be a lineage, conceivably, that goes all the way back to the early stages of life.
The dawn of time
In a world.
in the world. It's really old, like back to the very beginning of life on Earth?
To that era, yeah. I mean, maybe when cellular life was getting started. But the question is, well, what were the giant viruses like then? Now, some people have said, well, no, giant viruses actually started out as teeny tiny viruses, and they've just been like gathering up new genes through time and just been getting bigger and bigger and bigger. But, a number of the people who actually study giant viruses and have really, helped us to understand them most are saying, no, we don't think so. We actually think that these things started out as cellular life. They were cells. They were full-blown cells. And
Oh, you mean they were from the other side of the road? They were cellular life.
Yeah.
And then what, they switched sides?
yeah, they
What?
changed teams. Yeah.
How,
How? No, that, like, I can't have a plant that becomes an animal.
how did they? So they started off as like what we would call creatures,
Right.
And then
They started out truly alive. They
Like
they
freestanding out there in the air or the water or the
Yeah.
ground? Or
yeah, just some free-living microbe. Yeah.
and then
That
Well,
could-
then
that-
why would they be? Why would
then
you go
something-
demote yourself?
This is your problem with parasites. You keep saying mean things about parasites.
Well,
How many years have we been talking about parasites?
Wait,
Have
wait,
I
no,
taught
if-
you nothing?
If I had a choice between being having my own integrity and choosing to make a living on my own, or to suck off you, I would just live on my own. Excuse me for.
Hold on, this
I know
is-
you like parasites, but honestly,
Could you not use that passage in the recording, please?
it's already been cut.
Thank you.
So wait a second. So you, according to this theory, you have
it stands true nevertheless.
we have a microbe that is doing its thing, and then something happens.
Okay, but
What
listen,
is the something?
it becomes a parasite.
It becomes a parasite.
Or at least, maybe a symbiont. Basically what it does is it starts living inside another cell.
You mean it gives up its integrity as a free life form, a freestanding life form?
Wait, just so we understand what that means that it's got a shell, it's got a border, it's making its own energy, it's replicating in the way that
At the beginning.
At the beginning.
Yeah, at the beginning, it can make its own energy. It can grow. It can divide.
It can do all the things that living things do.
Yeah.
And then for some reason it chooses to require some other creature's existence for its own. It has to become dependent on some other organism for its very, very existence.
Well, let's flip it the other way and say it discovers a wonderful new home inside of another cell. It comes in and it's like
Just like I love leaving my Park Avenue apartment for a dark cave.
No.
It's a new and exciting opportunity.
No,
real
no,
estate
no,
wise.
no. Au contraire. Like imagine like let's imagine you're like Bear Grylls, okay? Let's imagine you are like hiking around and killing your own food, okay? Let's try to picture this, okay?
Robert doing this?
You're gutting your deer, you're starting your own fires, you're going on and on and on, and you do that for like a few years, and you're walking through the jungle, and
You're
then
very, very skinny because it's not going well.
So Robert Krulwich, the haggard hunter, and let's say you're doing this in Minnesota, right? So it's like cold, okay? And then suddenly, like, there's a break in the forest, and you come across a giant mansion, and you're like, what is this place? And you open the door, and inside there's like conveyor belts with ice cream and steak and and there are slippers waiting for you, and anything you need, it's somebody else is taking care of it.
There is one thing you left out. When I walk into this magical kingdom of soda, it doesn't let me out. I can't leave ever again because
Sure you can.
I am become so dependent on its natural wonders that I lose my independence, my integrity, and the very, very thing that I walked in with is now gone. I'm stuck
We did
inside.
literally have this conversation a few years ago.
We did. It's true.
We did, and
It's
I
true.
did point out to you at the time that you are quite dependent on other species. Do you want me to bring up?
No.
So I will just say see episode 32 or whatever.
And Chad's eyes will roll right out of their sockets.
So like being able to take advantage of another cell, evolutionarily speaking, is a great way to go. Because you have all these things taken care of for you. Now, and according to this theory, these mysterious ancient microbes started going into these cells and reproducing there, and then going out again, and then finding another host cell to infect. Okay,
Were they making their hosts sick?
probably, yeah,
Probably.
because giant viruses are not good to get.
Well, see, this complicates your mansion metaphor just a tiny bit because what it means is that you go in the conveyor belts and you're feeding yourself and you're having a good time, but then your filth starts to muck up the place and it starts to collapse from within. That doesn't sound so nice.
To strain the metaphor a bit,
Go, boy.
Robert
Oh,
Krulwich.
no,
Robert
don't even stop
Krulwich.
referring to me. Now it's going to him.
Okay,
No, I'm just trying to understand.
So you spend some time in this wonderful mansion. You rest. It's warm. It's comfortable. So on. You eat.
You fill it with your filth.
You start a family. And then all of a sudden you and your descendants, leave the mansion. The mansion just collapses from all the damage you did to it. But, actually you see in the distance there's another mansion. Let's just go over there. Now you feel like rested and ready and like, all we got to do is get over there. So let's just go there. We don't have to stop to kill a deer. We just go to that next mansion. The ice cream is waiting.
I still got to walk, so I need my legs, so to speak,
Sure.
to get to the next mansion.
Right.
But I don't need the powerful muscles that I would have needed to kill the deer. I can let
You
go of
don't
those.
you don't even need, let's say that you were, you don't even need the knowledge of how to kill a deer.
You could be blind, dumb, and fat.
So
That's where you end up.
these things
And destructive.
These
oh,
things
gosh, I'm so excited.
they start getting rid of these genes.
And how does that happen?
Just, a random mutation comes along and just cuts out a bit of DNA.
Because it doesn't need them.
You're fine. Yeah. You're like, that's okay. I mean,
Is it a moment where, oh, there goes a big chunk of me. Gone.
Yeah.
I don't need that.
I mean, that's a regular kind of mutation. That happens all the time.
Really?
In cells. Oh, yeah.
But then your successor being just travels a little bit lighter and is able to succeed just as well.
Right. So, if we are born, with a part of our DNA that's deleted that had some, like hemoglobin genes in it, like good night, like that's bad. I mean, but if you cut out a gene that this giant virus no longer needs because it's got everything supplied to it in its host, Fine. So let's chuck it out. So you have this. So the idea is that these viruses, they're giant viruses, but they're actually been shrinking.
Huh.
And
at a how fast does a giant imagining back at in the beginning there was not mega, not
being.
gyno,
No, in the
but
beginning there's a cellular being, right?
Oh, a cellular being,
yeah.
right? Okay, so this is
cellular being,
cellular
with
being,
all of
right.
the privileges and joys of independent life.
size-wise, it's a blimp. It's a massive thing. And then suddenly it starts to shrink bit by bit by bit by bit. At what rate does it start to shrink and shed itself?
Well, it could be that these giant viruses we're finding, these giant viruses that scientists are finding, could be shrinking very, very, very slowly. It could be that there are other viruses that made this transition that shrank faster. So maybe
It's a race to the bottom.
Maybe some tiny viruses are just former giant viruses that just shrank really fast.
Race to the bottom. It's such a different way of thinking about life. You generally assume, being a multicellular organism yourself, that little things in some deep sense, though you're not supposed to say this, want to be big things.
You don't want to say this.
I know. I know. But most people, unlike you, asshole, most people think that it's better.
I want in the podcast.
It's better to be more complex than to be simple. But here, you're talking about a different voyage altogether. That it might just work out for you to be simple rather than complex.
Well, given that viruses are insanely abundant on this planet, I mean, there are, by some estimates, 10 to the 31st power viruses on Earth. Think about that. Like it's a 1 with 31 zeros after it. I mean, it's inconceivable how many viruses there are on Earth.
So it's their world.
So apparently, nature has not agreed with you. But, it is interesting, thinking about how life gets smaller and simpler.
It is interesting, yeah. If it's true that this trajectory is as common as you say, that things start out big and then learn to live inside other things and in the process get smaller and smaller and smaller, and this is actually maybe what happens to a lot of viruses, not just some viruses, in a way it gives the virus an honorable history. I don't know why I feel that way.
Well, this boy isn't going to sign up for
No,
that.
he's not going to sign up for that, and I don't.
That's okay. Well, an honorable history, but then, I mean, it abandoned its free living past, right?
It did.
It gave in to the temptations of the mansion full of steak and ice cream.
It's true, but I've always assumed, and this is not something one should assume, that viruses were a kind of proto-organism. They were somehow at the beginning of something, and they never quite got going.
Yeah.
But you're actually saying that these viruses are, in a way, at the end, not at the end, but they're at the, I don't know how to quite use the words that I want to use. They feel somehow at the end of something, not at the beginning. Like you just took what I consider to be the beginning, and you've now made it an end.
An end.
Mm-hmm.
And that's interesting.
That's very interesting.
Yeah.
Very interesting.
So life can go in different directions.
And how far can that reverse journey go? I mean, can you go from how big did that? Was it ever like a turtle with things, or no, like a giant dinosaur? No.
No. Sorry.
No.
There are things I believe they're called mixozoans, which started out as free-living animals and have become parasites, and they're just down to just a few cells.
Wait. Mixozoans? You say when free-living animals, you don't mean animals in the way that
Animals.
anyone would think of an animal.
Like a jelly.
oh, look, my pet Fluffy. Not like that.
Well, my pet jellyfish.
Really?
Really?
Yeah.
So you're saying a jellyfish-sized thing has now reduced itself to a tiny speck?
A microscopic parasite of fish.
Get the
Don't even say it, because you can't do it if you're that small.
That's insane. Really? It's like going from something you can see and would want to avoid while swimming down to something that you might even just breathe in without even knowing it.
Mm-hmm.
Wow. Oh. You're blowing my mind. You're shrinking my mind.
What was it called again?
Myxozoan.
I believe they're
A
called
myxozoan?
Yeah.
How do you spell that?
Myxzoan.
I'm trying in my mind to construct a scenario where we, like the myxozoan, could begin to shed. Like if we were living inside the, like, not the iPhone, but the iHome, the iUniverse.
Well, but the fact is that we have cast aside some things.
What have we cast aside?
Well, we can't.
I mean, we used to smell
smell
better. I know
before.
that.
Smell better.
Yeah.
We used to be able to make our own vitamin C in our own bodies. Our own bodies were vitamin C factories.
Really?
Yes.
What changed that? Why did we want to let go of that? That sounds great.
Sunshine vitamin C.
Yeah, making your own supply of vitamin C. Well, if you are sitting around eating fruit all the time, fruit which is loaded in vitamin C, then if you get a mutation on your vitamin C gene, well, you're fine because you're getting your vitamin C from somewhere else. You don't feel that lack.
I see.
You don't start getting scurvy because you're feeding yourself on fruit, and then that mutated gene may then spread out and end up being in every member of your species, which seems to happen to us. I mean, you can literally see we have these broken vitamin C genes.
Huh. So sometimes we shrink too.
Yeah.
Okay, so there you have it, a raw conversation with science writer Carl Zimmer about shrinkage in life. Now, usually what happens in these conversations is because you're just talking and because you don't really have like an encyclopedia sitting right next to you, you get a lot of the little things wrong, little details, little facts, names, dates, whatever, and then, you fact check it later. So in fairness to Carl, as we were fact checking, we gave him the chance to listen back to the raw conversation, make a couple of amendments.
This is fact checker Carl, scolding, rambling Carl.
Okay.
We were saying that this microbiologist, Tim Robotham, took his samples to France, but actually there was another microbiologist named Richard Birtles that did it.
Gotcha.
So small but important.
Sorry, Richard.
Our apologies.
Yeah.
And Mamavirus turns out to have 1,023 genes, not 1,059 genes. My apologies. Then I started talking about Megavirus. At the time in 2011, it was indeed the biggest virus known. 1,120 genes, okay?
Okay.
However, there was in 2013 another virus found called Pandora virus. Now, I was saying that this was something found in the Siberian tundra. Wrong. This was found in the ocean. And this virus has a whole lot of genes.
How many?
It has 2,500.
Whoa.
2,500. I mean, that's way more than a lot of bacteria.
Also, at a certain point, we refer to Pandora virus as being the biggest virus in size. Actually, that distinction goes to Pithovirus. And also, it seems that since we talked, there's evidence that there might actually be a couple separate lineages of giant viruses. One may have evolved from big to small, as we talked about, but another one might have gone in the usual direction, from small to big.
There's one last thing that I see. So apparently I didn't quite spell myxozoan correctly. This is how you spell myxozoan. Myxozoan. Apparently I missed one of those O's. I can't remember.
I mean, I would be lying if I say I didn't think a little bit less of you now. Okay, extra O, back in.
The raw stupidity that goes into Radiolab. Yep. Stupid people interviewing stupid people.
About smart things. That's funny. That's a great tagline. Stupid. Okay. That's our new tagline. I'm Jad Abumrad. Thanks for listening.
Radiolab was created by Jad Abumrad and is edited by Soren Wheeler.
Lulu Miller and Latif Nasser are our co-hosts. Dylan Keefe is our director of sound design. Our staff includes Simon Adler, Jeremy Bloom, Becca Bressler, Ketty Foster Keys, W. Harry Fortuna, David Gable, Maria Paz Gutierrez, Sindhu Nyana Matt Keelty, Annie McEwen, Alex Neeson, Alyssa Jong Perry, Sarah Kari, Sarah Sambach, Ariane Wack, Pat Walters, and Molly Webster, with help from Timmy Broderick. Our fact checkers are Diane Kelly, Emily Krieger, and Natalie Middleton.
Hi, my name is Michael Smith. I'm calling from Pennington, New Jersey. Leadership support for Radiolab's science programming is provided by the Gordon and Betty Moore Foundation, Science Sandbox, the Simons Foundation Initiative, and the John Templeton Foundation. Foundational support for Radiolab was provided by the Alfred P. Sloan Foundation.